Parallel circuit, series circuit. How do we determine the capacitance of these two types of circuits? Hello, Sci-Pols! I am Ma'am Laorny Lachica, your science teacher for today. In this episode of Agham Alam Hub, we will differentiate the capacitance for parallel and series circuits. We will also calculate the capacitance for parallel and series circuits. Finally, we will appreciate the important capacitance applications in parallel and series circuits. In the next few minutes, we will explore science for another moment. Remember that a capacitor is a two-terminal electrical device that can store energy in the form of an electric charge. It consists of two electrical conductors that are separated by a distance. The space between the conductors may be filled by vacuum or with an insulating material known as a dielectric. The ability of the capacitor to store charges is known as capacitance. The capacitance can be determined by the ratio of the charge over the voltage of a capacitor. In symbol, we have C is equal to Q over V. Capacitors may be connected in a variety of applications. Multiple connections of capacitors act as a single equivalent capacitor. The total capacitance of this equivalent single capacitor depends on the individual capacitors and how they are connected. There are two simple and common types of connections, called series and parallel, for which we can easily calculate the total capacitance. Episode 3 of Agham Alam Hub describes and differentiates series and parallel circuit connections. Now, let us look at how capacitors are connected in a series circuit. This figure shows the series connection of the three capacitors with the voltage applied. Note that in this figure, opposite charges of magnitude Q flow to either side of the original uncharged combination of capacitors when the voltage V is applied. Conservation of charge requires that equal magnitude charges be created on the plates of the individual capacitors since the charge is only being separated in these originally neutral devices. The result is that the combination resembles a single capacitor with an effective plate separation greater than that of the individual capacitors alone, as you can see in this figure. A larger plate separation means smaller capacitance. It is a general feature of series connections of capacitors that the total capacitance is less than any of the individual capacitances. Charge on this equivalent capacitor is the same as the charge on any capacitor in a series combination. That is, all capacitors of a series combination have the same charges. Q sub t is equal to Q sub 1 is equal to Q sub 2 is equal to Q sub 3. This occurs due to the conservation of charge in the circuit. When a charge Q in a series circuit is removed from a plate of the first capacitor, it must be placed on the second capacitor plate and so on. We can find an expression for the total capacitance by considering the voltage across the individual capacitors. The potential across capacitors 1, 2, and 3 are respectively. V sub 1 is equal to Q over C sub 2, V sub 2 is equal to Q over C sub 2, V sub 3 is equal to Q over C sub 3. These potentials must sum up to the battery's voltage, giving the following potential balance. B sub T is equal to B sub 1 plus B sub 2 plus B sub 3. Potential V is measured across an equivalent capacitor that holds charge Q and has an equivalent capacitance C sub S. Entering the expressions for V sub 1, V sub 2, and V sub 3, we get Q over C sub S is equal to Q over C sub 1 plus Q over C sub 2 plus Q over C sub 3. Canceling the charge Q, we obtain an expression containing the equivalent capacitance C sub T of 3 capacitors connected in series. 1 over C sub S is equal to 1 over C sub 1 plus 1 over C sub 2 plus 1 over C sub 3. Let's try this. Find the total capacitance for the 3 capacitors connected in series, given their capacitances are 1, 5, and 8 microfarad. Entering the given capacitances into the expression for 1 over C sub S gives 1 over C sub S is equal to 1 over C sub 1 plus 1 over C sub 2 plus 1 over C sub 3. Let's substitute the given capacitance to our equation. 1 over C sub S is equal to 1 over 1 microfarad plus 1 over 5 microfarad plus 1 over 8 microfarad. This will give us 1.325 microfarad. Inverting the answer to find C sub S yields C sub S is equal to 1.325 microfarad is equal to 0.755 microfarad. This figure shows a parallel connections of 3 capacitors with a voltage applied. Here, the total capacitance is easier to find than in the series case. To find the equivalent total capacitance C sub P, we first note that the voltage across each capacitor is V, the same as the sources since they are connected directly to it through a conductor. Conductors are equipotentials, and so the voltage across the capacitors is the same as that across the voltage source. V sub T is equal to V sub 1 is equal to V sub 2 is equal to V sub 3. Thus, the capacitors have the same charges on them as they would have if connected individually to the voltage source. The total charge Q is the sum of the individual charges. Q sub T is equal to Q sub 1 plus Q sub 2 plus Q sub 3. Using the relationship Q is equal to C times V, we see that the total charge is Q is equal to C sub P times V, and the individual charges are Q sub 1 is equal to C sub 1 times V, Q sub 2 is equal to C sub 2 times V, and Q sub 3 is equal to C sub 3 times V. Entering this into the previous equation gives C sub P times V is equal to C sub 1 times V plus C sub 2 times V plus C sub 3 times V. Canceling V from the equation, we obtain the equation for the total capacitance In parallel, C sub P is equal to C sub 1 plus C sub 2 plus C sub 3. Total capacitance in parallel is simply the sum of the individual capacitances. Let's try this. Let's find the total capacitance for 3 capacitors in the previous example, but this time connected through a parallel circuit with their capacitances are 1, 5, and 8 microfarad. The total capacitance in this parallel connection would be the sum of the individual capacitances, 1 microfarad plus 5 microfarad plus 8 microfarad, that would be equal to 14 microfarad. The most common use for capacitors is energy storage. A great example of this is batteries. Additional uses include power conditioning, signal coupling or decoupling, electronic noise filtering, and remote sensing. Because of their varied applications, capacitors are used in various industries and have become a vital part of everyday life. In this episode of Agham Alam Hub, we calculated the capacitance of capacitors connected through parallel and series circuits. For a series circuit, the charge is constant, while the voltage is determined by the sum of the voltage of the different capacitors in the circuit. While the formula can be determined the total capacitance, 1 over C sub S is equal to 1 over C sub 1 plus 1 over C sub 2 plus 1 over C sub 3 and so on. On the other hand, for a parallel circuit, voltage is constant. The total charge can be determined by the sum of all the charges in the circuit. The same goes for the total capacitance, which is the sum of individual capacitances in the circuit. C sub P is equal to C sub 1 plus C sub 2 plus C sub 3 and so on. The most common use for capacitors is energy storage. A great example of this is batteries. Additional uses include power conditioning, signal coupling or decoupling, electronic noise filtering, and remote sensing. Because of their varied applications, capacitors are used in various industries and have become a vital part of everyday life. That's all for today's iPulse. Don't forget to like, share, subscribe, and turn on the notification bell. See you again next week for another moment. Only here in Agham Alam Hub, Palajan's SciTech Portal. Bye!